Hey everyone, welcome to the second part of my video on doing volumes by cross sections. And last time we kind of left off with this idea that we're going to keep these three views in mind. We're building up cross sections from our base region with a certain shape, maybe squares or triangles or semicircles. And we want to keep in mind these are coming up from that base region that's right there. So finding the length of our edges on that base region is going to require, the same thing that we did when we were looking at area or centroids, breaking this up into rectangles and computing some lengths across those. And then also this just general cross section, right? So we got a rectangle across the bottom, but in the case of a square, it's nice and easy. Find the volume of this. With triangles, it's a little more difficult depending on the shape of the triangle. If it's equilateral or a right triangle, or some of those will be easy, some of those won't. And then semicircles, again, just different. So keeping that specific shape in mind is going to be important. All right, so let's go and do a couple of those. So here we're considering the volume with the base region that's the same as we had before. Y is 1/3 x plus 6, y is 1/9 x squared. Cross sections perpendicular to the x-axis are equilateral triangles. So rather than squares, we have this equilateral triangles that's right there. So we're going to put in some sample rectangles. It's like we did before. So a couple rectangles, maybe something like this coming up, and keep in mind these are going to be these equilateral triangles. That might not look equilateral, but let's go with it. All right, so equilateral triangles coming out from that plane. So these would be like actually pointing toward you. So what they would look like. The first thing we're going to do is look at our thickness, right? So the thickness of this little edge that's touching our base region, right? That thickness is going to be a little dx right there. So thickness we would say is dx. Rewriting the base b in terms of x. So that's very similar to what we had before. Our b is just going to be that y1 minus y2, or replacing those with our definitions in terms of x, that 1/3 x plus 6 minus 1/9 x squared. All right, and this is the tricky part now, the volume of this triangle. So what's the volume of this cross-sectional slice? And I'm going to try to leave everything in terms of b, and then I'll just replace that b on the last part when I'm doing the integral. So I just want to keep things in terms of b for this step. So we know across the bottom, right, this whole edge right here, that corresponds to these edges right up here from the line to the parabola. So those are b. But now we want, if we're thinking of a triangle, 1/2 base times height, we really would be nice if we had that height right there. So I'm going to go and put in that area, base times height, and we'll go ahead and multiply by the thickness to get the volume at the end. So looking at an equilateral triangle, if I drop that height, we have a couple things we can think about here. One is that inside, this is just going to be half the base, right? This diagonal length, since it's equilateral, is also b right there. And then there's two ways you can think about it. One is I can use some trig, right? This would be 30 degrees right here. If it's equilateral, our angles are all the same. So 60, 60, and 60 across all of these angles. And this one's cut in half, so 30 up there. I can use some trig to get this other side, which we're going to call that h. Or I could do Pythagorean theorem with 1/2 b this b and that h. So there's two ways you could go. Either way should work out. I'm going to do the trig part. If you want to try Pythagorean theorem, you can. You should get the same answer in the end. So right now I'm just trying to find that h. So h would be the opposite of the 60-degree angle. Hypotenuse would be b, so kind of h is a height and h is hypotenuse kind of gets weird, but anyway, we'll just keep going with that. So I have h over b. This is my opposite over hypotenuse. So that's going to be the sine of 60. So we'll say sine of 60 is h over b. So just multiply by b, and we get b times sine 60 is our h. So this type of thing works no matter what type of triangle I might have with maybe some weird angles or stuff like that defined. I could still use this type of idea. Pythagorean theorem, again, should also work as long as you got a couple of known sides on those guys. The sine of 60, that should be one we know, so I believe that is square root of 3 over 2 times that b. So this is our height. So we'll go ahead and replace that right in there for that area. So we got area is 1/2 times base times our new height, which is the square root of 3 over 2 times b. And I'll just leave it like that for now. And we'll go ahead and simplify that a little bit. So this is going to be 1/2 times root 3 over 2. It'll be a square root of 3 over 4. And then b times b would be b squared. So that's my area. My volume is going to be the same thing, but times my thickness, which is my dx. So we're going to say this is square root of 3 over 4 times b squared times dx. And if you want to replace things in, that's going to be kind of what we do on the next part. So this, we just want to use variable b. We'll leave it in terms of b. And then we'll go ahead and replace that with either the y1 minus y2 or this longer expression that's up here. So let's go ahead and put that in. We're going to do our integral from -6 to 9. So that was, remember from up here, we're starting at -6, going all the way to 9. So those are my intersection points. And then we'll do this volume of that triangle. So square root of 3 over 4 times b squared, and I'm just going to replace that b with y1 minus y2 squared, and then dx. And again, I can replace those y1, y2s just like I had up here. If you want to put those in and do it by hand, you can, but I'm just going to evaluate that over on Desmos. So over here on Desmos, we have our same y1, y2 definitions. Really the only thing that's changed is I get this root 3 over 4 in front of this y1 minus y2 squared. So we get 135.316 something or other. So I'll just say 135.32 and go and put that in. So we got 135.32. Now, the hardest part of this one was basically this part right here, finding the volume of that slice. So some of them are super easy, like squares. Some of them, like equilateral triangles, you have to work a little bit harder on those. So it all kind of depends on your shape, how complicated that's going to get. All right, let's see. Let's do one more here at the bottom. Same region, but with semicircles. So we go ahead and just kind of sketch in our region like we had before. All right, so we had some shape that was like this, and we had our rectangles coming this way. So we're talking something like that coming out. And this is our same 1/3 x plus 6 on the top, 1/9 x squared on the bottom. Still going from -6 over here to 9. The only difference is going to be the shape, right? So if I go ahead and think about that semicircle, right, what is the volume of that semicircle that I'm going to get? All right, well, I know entire circles, right, are pi r squared. We're only going to get half of that. So I'm going to say this is 1/2 pi r squared, where r is the radius coming out this way, right? So this is my r. But really, what is this whole length right here? This whole length corresponds to what we normally have been calling, right, b. So that's my base right there. So I'm going to try to get this all in terms of b, because I know b is just the y1 minus y2. So let's go ahead and try to get that in terms of b. So r is really half of b right here, right? So b is across the whole thing. R is going to be half of that. So let's go and replace that in there. So we get 1/2 pi times half of b quantity squared. And when I square that, I'm also squaring the 1/2 and I'm squaring the b. So this is really 1/2 times pi times 1/2 squared, which is 1/4, times b squared. And then 1/2 times 1/4 is 1/8, and I got a pi, so we'll say this is going to be pi over 8 times b squared. And if you want to think of this as a volume, then I can also multiply by that dx. So this is the volume I want to add up. Notice a lot of times you're going to get these b squareds. That's because you're essentially just looking at the face, which is going to be some relationship of b squared, right? I got a b talking about an area, so b squared, but maybe just a fraction of the whole, b that's being squared. So not an entire square this time, just a semicircle. So pi over 8 times b squared. Add all these up, right? So we got all these semicircles coming around, this region in here, and we're just going to add them all up over that whole space. So integral from -6 to 9 is where my x's are going to run. And we got our pi over 8. Our base, again, is this y1 minus y2. And that's going to get squared. And then the dx, that's the thickness. So go ahead and compute that out. Again, I'll just do that over in Desmos real quick. So pi over 8 rather than a √3 over 4. Our pi, there's our 8. So I get 122.72. I'll say this is 122.72. So that is the general idea of most of these when you're going to be computing these out, looking at what is the volume of these guys. That's really what you kind of want to be thinking about is what are the areas of these cross sections and how can I get that. Real quick on this guy. What would likely change if you use slices parallel to the x-axis instead of perpendicular? Would it change the shape of the solid, the volume of the solid, or both? So I'll let you think about that. Pause the video and then we'll have the answer here in a second. Alright, so the answer to this may not be intuitive. The answer is actually both will change. The reason for that is that if you think about your cross sections, these over here on the left, if they're running for this shape perpendicular, are not going to be as long as these over here if they're running parallel to the axis. So if it's parallel to the x-axis, we're going to get much larger, right, squares that are coming up if we're doing squares on that one than we would on this one where the longest is right here, but not nearly as big as this one. So it actually changes both the shape and the volume on this one. So sort of weird, a little bit different than revolutions. Again, on these, if you want to take a look at the last page, there's some homework there. So go ahead and try that, and that'll do it for this video.